In this video here, we're going to take a look at the midpoint method. Now, we mentioned in the previous video that one way to improve the accuracy of our numerical solutions to first order differential equations was to use a modified version of Euler's method, and this is known as the midpoint method. So the midpoint method for finding approximate solutions to first order differential equations uses the following approximation here. So dy by dx at x equals x naught is approximately y1 minus y subscript minus 1 all over 2h. And again, it's often just easier to write this as an iterative formula. So if we do that, then we obtain this result here. Now again, just as we saw with the previous video here for Euler's method, these results here, so this approximation and this iterative formula here, are not given in the formula book. But the good news is, for an exam style question based on the midpoint method, you will often just be given this approximation here. Okay? So in terms of an introduction here to the midpoint method, we don't need too much more, right? We are just basically building on what we introduced in the previous video for Euler's method. And as we already mentioned, the midpoint method is just a refinement or a modified version of Euler's method. Okay? So let's just work through an example together here for the midpoint method. So let's just have a go then at this one practice question here for the midpoint method. So for this question here then, we're told that a particular solution to this given differential equation here passes through the point 0, 1. Now for the first part of this question, we need to verify that the approximation formula given here with a step length of 0.5 gives y1 is equal to 1.5. So for the first part of this question anyway, this is just simply an application of Euler's method. Okay. So let's just note then for part A here, that x0 and y0 are already given. So x0, y0, that would simply be 0 and 1 here. Like so. We also have the step length, right? So h here equals 0.5. So h is equal to 0.5 here. So the first thing that we need to find then is dy by dx at x equals x0. Okay. So dy by dx here at x equals x0 is equal to, so we can easily obtain this then by using this given differential equation here and just substituting in the values then of x0 and y0. So xy is 0 times 1 plus y, which is 1, all over y squared, so that's 1 squared, minus x, which is 0. Okay. And if we simplify this here, then nice and straightforward, we get left with 1 over 1, which is just 1. Okay. So that gives us dy by dx at x equals x0. So for y1 then, so for y1 here, hopefully nice and straightforward, this will be equal to y0 plus h times dy by dx. That's x equals x0. Okay, like so. So what does this give us here then? Well, y0 is 1. So this is 1 plus h, which is 0.5 here. 0.5 times by dy by dx at x equals x0 here, which is 1. Like so. So we get 1 plus 0.5 here, which is equal to 1.5 as required, right? That's equal to 1.5 as required. Okay. So that gives us the solution here to part A. Now for part B, then it says use the formula given here with a step length of 0.5 to obtain an estimate of the value of y when x equals 1. So now for the next part here, we're now using the midpoint method. Okay. And don't forget then that the midpoint method here is a refinement of Euler's method. So for y2 here then, for part B, so for part B here, y2 is equal to, so y2 is equal to y0 plus 2h times by dy by dx at x equals x1. Okay, so to find this here, we obviously need to do part A, right? So if you ever get a question based on the midpoint method, and it doesn't structure the question in such a way here where using Euler's method is, immediately obvious for the first part of the question, that's something that you need to be able to deduce yourself. Okay. So for dy by dx then, or dy by dx here, x equals x1, this will be equal to, so what I'm going to do here then is just note that x1 and y1 are given as, so x1, y1 here. So x1 would be x0 plus h, so that's going to be 0.5 here. So we get 0.5 for x1, and now for y1, that's 1.5. Okay. And even if you couldn't establish this first part of the question here, because we have y1 and x1 is, simple enough to deduce, you can still go on to attempt part B here. Okay. So dy by dx then at x equals 1, that would simply be, so it's going to be xy here, so that's going to be 0.5 times by 1.5. We then have plus y here, so plus 1.5. And this is all over. So it's going to be 1.5 squared minus then 0.5. Okay. So just use your calculator here to evaluate this. Let me just quickly grab mine. So let's just quickly do this here. So 0.5 times by 1.5 plus 1.5 here. That gives me 2.25 for the numerator. For my denominator here then, 1.5 squared minus 0.5 gives me 1.75. 1.75 there. So 2.25 all over 1.75. So not the nicest number here. So I'll give it an exact form. So this is 9 over 7. Like so. So rather than writing this as a decimal, let's just keep it in exact form. Okay. So we now have everything I need then to find y2 here. Okay. Or to find an estimate for y2. So in that case then, y2 is equal to, so y0 here, which is 1. So we have 1 plus, so we have 2h here. So h is 0.5. That's 2 times 0.5. And then we times it by dy by dx at x equals x1, right? So in that case then, we have 2 times 0.5 times 9 over 7. So again, just use your calculator here to evaluate this. If I quickly do this then, so I've got 2 times 0.5, which is 1, times 9 over 7. So I just get 9 over 7 right. And then plus 1. So what this gives me here then is 16 over 7. So what I do here then is give this as a decimal. Now it doesn't specify a degree of accuracy here. So let's just give this to, say, 3 significant figures. Okay, so when x equals 1, here, y is equal to 2.29 here. Okay, and that is to 3 significant figures here. Like so. Okay, you could also just note this here as x2 and y2. So x2 is 1 and y2 is this here, so 2.29. Okay, that's also fine as well if you want to give the answer like that. Either way, you should obviously get the same here for y. So y equals 2.29 there, to 3 significant figures. So there we have it. That gives us the solution to this one practice question for this video here. And that actually brings us to the end then of this video here on the midpoint method.